This year, ICRA asked us to think about the future of work. I believe that the future of work involves collaborative robots that are able to quickly identify approximate values for the inertial parameters of manipulated objects, making them effective in unstructured environments. For safety reasons, collaborative robots move at a limited velocity that is defined in ISO standards. This low speed greatly hinders identification algorithms which are forced to deal with signals of low amplitude but with significant noise. As a consequence, the identification of the inertial parameters of a manipulated object is typically slow and inaccurate. We made the key observation that gravity dominates fictitious forces in cobots' velocity regime. Neglecting the fictitious forces produce a reduced model of the dynamics that should be fairly accurate at cobots' velocity regime and not hindered by low signal-to-noise ratios in velocity and acceleration data. Unfortunately, the identifiability of the inertia tensor is lost when relying only on this reduced model. Ideally, we'd like to use the reduced model for undynamic motions when signal-to-noise ratios are terrible and otherwise use the full model. So we combine both models through a weighting scheme where a weight W increases with a measure of the motion dynamism based on the amplitude of the acceleration and velocity signals. Additionally, the shape of the manipulated object is discretized with point masses. A critical advantage of this representation is that the physical consistency of the inertial parameters is guaranteed as long as the point masses are positive. An optimization is performed over the point masses with three terms in the objective function. The first term defines a cost that encourages the usage of the reduced model in more static situations, while the second term defines a cost that incentivizes the usage of the full model in more dynamic situations. The last term encourages mass homogeneity and is needed to obtain a unique solution in static situations. And the optimization problem is subject to mass positiveness constraints. The resulting identification algorithm was tested with a real robot manipulating a modular test object in which weights were placed in a few different configurations. Ground truth inertial parameters can easily be computed for any configuration of this test object, making it practical to perform real-world experiments with intricate mass distributions. Results suggest that our proposed algorithm is better suited to cobots' velocity regimes compared to some other classical and state-of-the-art algorithms. These performances are achieved by guiding the identification with a reduced model and leveraging information about the shape of the object. If you enjoyed this brief overview of our work, feel free to look at our paper or to contact us.